It's on a scale that's hard to take in. The size of 600 football pitches, this colossal construction site is where a record-breaking tunnel is being built, running 18 kilometres under the Baltic Sea.
Beneath the muddy waters of one of Asia's most volatile rivers, a silent revolution unfolded, one that shattered records, redefined limits, and turned a city's greatest obstacle into its boldest opportunity. At first glance, it sounds impossible. An underwater highway megastructure completed in just 110 days. Not planned, built. But this isn't just a story of speed. It's a blueprint of precision, pressure, and purpose. What sparked it wasn't ambition, it was desperation. What followed wasn't a miracle, it was something far more engineered. Hidden deep within this feat is a move so counterintuitive, so daring, it forced planners to go where no bridge could ever reach. What do you build when the surface betrays you and time won't wait? In the heart of China, one city found its answer not above the river, but far beneath it. And what they created down there, you'll have to see it to believe it. The crisis that sparked a mega project. For nearly a decade, Jinan's traffic congestion ranked among the worst in China, despite being a rising economic hub in eastern Shandong province. The city's urban infrastructure simply couldn't keep up with its breakneck growth. By 2020, Jinan's vehicle ownership had surged past 3.5 million, more than one car for every 3 residents, and that number continued to climb with each passing year. Streets built for a much smaller population now carried traffic volumes more than double their designed capacity. As delivery trucks, ride-hailing vehicles, and private cars competed for the same outdated lanes, entire districts experienced daily standstills that paralyzed mobility and productivity. This paralysis hit hardest at the Yellow River, which slices the city into northern and southern halves. Though both areas were experiencing rapid urbanization, the infrastructure linking them was dangerously outdated. The 2 primary bridges, built decades earlier, were never meant to accommodate modern urban traffic loads. And with no rapid transit alternatives, even minor accidents or weather disruptions at a bridge crossing triggered citywide gridlock. This vulnerability became glaringly obvious during major holidays, when multi-hour delays spilled deep into city streets, freezing economic activity and emergency services alike. The stakes were more than just inconvenience, they were economic and strategic. Jinan's urban development blueprint heavily emphasized the revitalization of its northern districts, which offered space for logistics hubs, industrial parks, and residential sprawl. But without fast, high-volume transit options, those areas remained disconnected from the urban core and underinvested. Companies hesitated to expand across the river, housing prices lagged, job creation slowed. Transportation experts estimated the direct cost of traffic congestion to be over $2.3 billion annually, factoring in fuel waste, lost work hours, and supply chain inefficiencies. For a city aiming to be a regional innovation leader, this bottleneck wasn't just a nuisance, it was a systemic risk. In response, city planners knew a stopgap fix wouldn't cut it. Widening roads or building more bridges might buy a few years of relief, but not the multi-decade scalability Jinan needed. After 5 years of feasibility studies, simulations, and international consultations, one bold solution emerged as the front-runner: a massive underwater highway tunnel beneath the Yellow River, capable of channeling tens of thousands of vehicles daily with minimal surface disruption. The decision wasn't taken lightly. It required rethinking urban connectivity, engineering ambition, and political will. But by early 2023, with public pressure mounting and economic costs compounding, the tunnel was no longer a concept. It was a priority. The city was ready to dig its way out of crisis and into a new era. But as bold as the tunnel plan sounded, one critical question remained: why not just build another bridge? Why building a bridge wasn't an option? When planners first confronted Jinan's traffic paralysis, the most conventional solution on the table was to build more bridges. After all, bridges had historically connected cities across rivers, and the Yellow River already had 2 such structures in place. But what seemed like the most straightforward fix unraveled under closer inspection. The Yellow River, nicknamed China's Sorrow for its volatility, presented a host of natural and man-made constraints that made bridge expansion not just impractical, but potentially disastrous. Engineers studying the river found that its banks were some of the most geologically unstable in the country, shifting by meters during seasonal floods. Identifying a safe, stable location to anchor a new bridge was nearly impossible without risking structural compromise or future collapse. These environmental uncertainties were only the beginning. Much of the Yellow River's course through Jinan is designated as a Class 1 ecological protection zone, home to a diverse and fragile aquatic ecosystem. Bridge construction in such areas would have required massive dredging for deep foundation pilings, an act that would churn up sediment layers vital to the health of over 160 native fish species. Disruptions of this kind would not only risk long-term damage to biodiversity, but also violate strict national environmental regulations, placing the city's infrastructure ambitions in direct conflict with conservation mandates. The pressure to modernize was real, but so was the legal and ethical obligation to protect the river. Beyond the river itself, Jinan's dense urban fabric posed yet another obstacle to new bridge construction. On the city's southern bank, the only possible bridge approach routes ran through some of its most heavily developed neighborhoods. These zones weren't abandoned industrial lots. They were residential communities, schools, and businesses. Constructing a new bridge here would require the forced relocation of an estimated 240,000 people and the demolition of entire city blocks. The cost of this urban upheaval was projected in the billions, not just in terms of money, but in social trust and political stability. City leaders knew that displacing 250,000 people for a bridge was not just unsustainable, it was politically untenable. Faced with insurmountable technical, environmental, and human costs, Jinan's planners realized they needed a fundamentally different approach, one that avoided both the instability of the river's surface and the disruption of the communities above it. That's when the idea of an underwater tunnel gained traction. Unlike a bridge, a tunnel could pass silently beneath the riverbed, leaving ecosystems untouched and neighborhoods intact. More importantly, it offered the flexibility and scalability needed for a rapidly growing metropolis. The tunnel proposal wasn't just a bold move, it was a rational response to a complex urban dilemma. Going underground wasn't about extravagance, it was about survival. Inside the double-decker tunnel layout. From the outset, the Jinan-Huanggang Road Tunnel was never going to be a conventional infrastructure project. Engineers faced the enormous challenge of threading a high-capacity highway through one of China's most geologically volatile rivers without disturbing life above or below. With limited room to expand horizontally beneath the unstable Yellow Riverbed, the team turned to vertical innovation, opting for a rare double-decker tunnel configuration housed within a single circular bore. But capacity wasn't the only goal. Efficiency and safety were baked into every meter. The tunnel employs a unidirectional flow model on each level to eliminate the risk of head-on collisions and ensure smooth, uninterrupted traffic. AI-driven traffic control systems dynamically manage inflow, adjusting timing and entry rates based on real-time congestion levels. The result? A tunnel that prevents backups before they even begin. Inside, the environment is designed to feel less like a cavern and more like a controlled, high-tech corridor. Low-glare LED lighting simulates daylight to reduce driver fatigue, while anti-skid pavement coatings and reflective lane markings boost visibility and reduce accident risk, especially in wet conditions. Emergency exits are spaced every 200 meters, linking both decks to pedestrian escape routes housed in the crown of the tunnel, well above potential flood zones. The tunnel's structural integrity had to match its ambitious design. To distribute the immense load, hydrostatic pressure from the river above, seismic shifts, and non-stop traffic vibration, engineers relied on finite element modeling to simulate stress cycles decades into the future. A central structural spine was embedded between the decks, acting as a reinforced core that carries vertical pressure alongside the outer ring. Each component was engineered for redundancy, ensuring the tunnel could safely handle increased loads for generations to come. What emerged wasn't just a clever use of space, it was a tunnel that redefined underground highway design. Wide enough to hold two roadways, smart enough to regulate itself, and strong enough to withstand the might of the Yellow River above, the Huanggang Road Tunnel is more than an escape from traffic. It's a glimpse into the future of urban mobility. Engineering for high stakes. Building a 5.8-kilometer, 6-lane tunnel beneath one of China's most unpredictable rivers in just 110 days wasn't just ambitious, it bordered on the impossible. But from the outset, the Jinan-Huanggang Road Tunnel project wasn't about choosing between speed and safety, it was about mastering both. The tunnel is being constructed in carefully managed phases, with the full 5,755-meter length set for completion in late 2025. But the most critical portion, the 3,190-meter underwater shield section that runs directly beneath the Yellow River, was completed by the end of 2024 in just 110 days. That's not just fast, it's a new world record for a tunnel of this scale and complexity. The achievement pushed global benchmarks forward, proving that rapid construction doesn't have to come at the cost of structural integrity or safety. From the very beginning, safety was treated as a design mandate, not an afterthought. Every element of the tunnel's construction was engineered to account for the high-pressure environment below the river, the risk of fire, flooding, and even seismic disruption. The tunnel's emergency response framework is one of the most advanced ever installed in an urban infrastructure project. Vertical escape shafts were placed every 200 meters, linking the upper and lower traffic decks to protected pedestrian walkways situated in the crown of the tunnel, safely above the highest flood risk zones. Each walkway connects to anti-backflow exit hatches, ensuring a safe escape even during water ingress or fire. Speaking of fire, the tunnel interior was coated in fire-resistant materials, with automated water mist suppression systems designed to extinguish flames quickly while maintaining visibility, a crucial element in any confined vehicle-heavy structure. These systems were layered with AI-based fire detection, creating a responsive, multi-tiered defense system ready to adapt in real time. Then there's the air you breathe. In long tunnels, air quality can become a silent hazard, but not here. The Jinan Tunnel features a ventilation system with 16 jet fans per kilometer, constantly replacing air every 3 minutes. In case of a chemical spill or fire, the system can instantly reverse airflow, pushing smoke or toxic gases away from evacuation routes and giving responders and drivers critical time to escape. Embedded sensors track CO2, temperature, and airflow speed, auto-adjusting fan settings to maintain safe, breathable conditions around the clock. Perhaps the most futuristic system of all is the tunnel's AI-powered traffic regulation system. Instead of relying solely on static signage, this intelligent network adjusts the rate at which vehicles are allowed to enter the tunnel, depending on traffic density, weather, or emergency conditions. Combined with adaptive lighting, which responds to vehicle flow and speed, the system helps prevent congestion and improves driver reaction time, especially crucial when traveling at 60 kilometers per hour through a tightly confined space. Ultimately, the Jinan-Huanggang Road Tunnel proves that speed doesn't have to mean sacrifice. While the project smashed records with the completion of the underwater segment in just 110 days, it also set new standards for safety, control, and long-term reliability. This tunnel wasn't just built fast, it was built to outlast and outperform expectations in every possible way. Precision under pressure. Deep beneath the Yellow River, where pressure, sediment, and unpredictability reign, one machine stood between chaos and progress: Shanhei. Meet Shanhei, a Herrenknecht-built mixed-shield tunnel boring machine, TBM, custom-engineered specifically for the Yellow River's chaotic subsoil. Measuring a colossal 17.5 meters in diameter, roughly the height of a 5-story building, and weighing over 200 tons, it is one of the largest and most powerful TBMs ever deployed. With a price tag estimated at $80 million, Shanhei is a machine built for high-stakes engineering. Its core powertrain delivers an astonishing 7,610 horsepower, 5,600 kilowatt, and over 25.8 million pound per feet, 35,017 kilonewton meter of torque, enough to chew through some of the most unstable geology on Earth. But sheer muscle wasn't enough. The Yellow River's underbelly was a volatile mix of soft soils, shifting groundwater, and crushing hydrostatic pressure. To survive and succeed under such conditions, Shanhei relied on advanced intelligence and design. It was equipped with more than 3,800 sensors, feeding real-time data on soil pressure, moisture, torque resistance, and cutter wear into an onboard AI system capable of adjusting cutter head speed, hydraulic pressure, and angle within milliseconds. To maintain pressure balance during excavation, particularly under depths where pressure climbed to 7.5 bars, Shanhei used an automatic air cushion system inside its excavation chamber. This allowed the TBM to safely carve forward without triggering a collapse or sudden blowout. A telescopic camera system monitored the cutting head during operations, reducing the need for dangerous hyperbaric maintenance interventions, a common risk in pressurized tunnels of this scale. This adaptability was tested frequently. When Shanhei encountered a surprise granite boulder 12 meters below the riverbed, it triggered an instant recalibration, adjusting torque output and hydraulic pressure in less than 8 seconds, an adjustment that would take human crews hours. In another instance, when shifting groundwater threatened stability, Shanhei's smart systems adjusted cutting angles and pressure to maintain tunnel integrity and avoid delays. But Shanhei didn't just dig, it built. Every 2 meters, it paused briefly to install a 72-ton concrete ring made of 10 interlocking segments. These rings formed the tunnel's structural skeleton, locking in behind the cutter head like armor. Laser alignment systems ensured each segment was positioned with a margin of error under 5 millimeters, a staggering feat over a 5.8-kilometer tunnel path. Keeping Shanhei moving at optimal speed required a finely tuned logistics engine. The machine had 432 cutter teeth, each needing replacement after just 35 meters of progress. Crews rotated in 12-hour shifts to inspect, service, and replace components with modular efficiency. Predictive maintenance systems minimized downtime, averaging just 22 minutes per cycle, even in extreme underground conditions. Inside, over 3.8 kilometers of active cabling carried power and telemetry data throughout the machine. Everything was ruggedized, protected from vibration, moisture, and shifting ground. Shanhei's control center operated like a mobile mission command, where engineers could adjust settings like torque and temperature in real time without ever halting progress. And progress is where Shanhei shattered records. The TBM maintained a daily advance rate of 16 to 18 meters, even through the Yellow River's most unstable sections. This pace didn't just exceed expectations, it set a new world record for shield tunneling in its class. Shanhei wasn't just a piece of equipment, it was a precision-engineered survival system designed to perform in conditions that would crush lesser machines. In the battle beneath the Yellow River, it didn't just dig a tunnel, it carved a new standard for what mega TBMs can accomplish when faced with geological chaos and extreme pressure. Even with Shanhei's unmatched precision carving through the earth, the true test lay ahead, assembling an entire megastructure at a pace that defied global norms. Assembling a subterranean giant. Completing a 5.8-kilometer highway tunnel would be ambitious under any circumstances, but doing it beneath a volatile riverbed and finishing the most complex segment in just 110 days made history. Tunneling officially began on September 1st, 2024, and by December, the entire 3,290-meter underwater shield segment had been bored, sealed, and structurally reinforced. This milestone included the installation of 500 precision-engineered concrete pipe rings, each aligned within millimeters to ensure absolute structural stability. With this feat, the project set a world record for the fastest construction of a large-diameter underwater tunnel segment. The speed was made possible through a construction model that prioritized prefabrication and automation. About 92% of the tunnel's components were built off-site in controlled facilities, ensuring quality and minimizing delays due to weather or soil unpredictability. On-site, an 18-kilometer temporary rail network delivered materials, tools, and personnel directly to the TBM's cutting face. Assembling Shanhei took only 14 days, and once operational, it ran 24/7, with crews in rotating 12-hour shifts. Every 2 meters of progress triggered a rapid 38-minute pause for installing a 72-ton tunnel ring, after which the machine advanced again, turning days into meters with machine-like discipline. To maintain this momentum, engineers managed a high-speed supply chain at industrial scale. As many as 14 concrete deliveries per hour were synced with Shanhai's pace. During night shifts, technicians tackled maintenance, replacing cutter teeth, recalibrating hydraulics, and monitoring 3 kilometers of active electrical cabling embedded within the TBM. The coordination was exacting. While one crew rotated components on the cutter head, another staged new rings, ensuring that downtime rarely exceeded a few minutes. This operational rhythm kept Shanhai boring at record pace, even as conditions above and below ground remained anything but stable. Weather too posed a formidable test. In October, torrential rains threatened to swamp access roads. Crews deployed emergency pumps, diverting 12,000 cubic meters of water in under 9 hours. Then, in November, with temperatures plunging to -7 degrees Celsius, engineers preheated grout mixtures to 35 degrees Celsius to prevent curing defects. Yet, progress never stalled. And as of April 2025, construction moved above ground, with the first elevated pillars of the Longhu interchange section completed, a key structural node that signals the final phase before full tunnel integration later this year. What began beneath the Yellow River is now rising above it and racing toward the finish line. When the river fights back. Beneath the Yellow River lies a geological minefield, a shifting mix of sand, silt, clay, and waterlogged sediment that behaves more like quicksand than solid ground. Unlike tunneling through rock, this soft, unstable material posed a constant risk of collapse, flooding, and machine entrapment. The pressure from the river above only made things worse. At its deepest point, external forces reached 580 kilopascals, enough to crush an unreinforced structure like a tin can. From the outset, engineers knew that navigating this ever-changing terrain would be one of the most formidable challenges of the entire project. To counter these conditions, the Shanhai TBM was designed not just to bore, but to continuously reinforce the tunnel behind it, like a 3D printer laying structural armor as it advanced. Each 2-meter segment was immediately lined with a 72-ton concrete ring, locking in place with near-millimeter precision. But even with this constant reinforcement, soil variability introduced major risks. One moment the machine would be cutting through hard clay, and the next it would plunge into loose, water-filled sand. These abrupt shifts could destabilize the tunnel path or cause the machine to lose traction altogether. The TBM's sensor array played a crucial role in anticipating and responding to these changes. Thousands of data points, from pitch levels and water ingress to torque resistance, were monitored in real time. When anomalies appeared, such as sudden drops in pressure or unexpected material resistance, the system's AI would make instant hydraulic adjustments to stabilize cutting angles and regulate force. In one particularly volatile section, engineers faced a sudden inflow of water from a hidden fault line. Thanks to the TBM's quick adaptation and the pre-installed drainage controls, they were able to seal off the breach without halting progress. Still, not all challenges could be predicted. Some areas required manual intervention and on-the-fly problem-solving. In regions where the soil composition shifted too rapidly for the TBM to adjust in time, engineers developed a foam injection system that temporarily solidified the ground ahead of the cutter head, giving the machine a stable surface to bite into. These innovations didn't just keep the tunnel on track, they led to multiple engineering breakthroughs, including new soil treatment protocols and adaptive boring strategies. In many ways, the Yellow River fought back, but the project's greatest strength was its ability to fight smarter, minimizing the river's ecological footprint. While the Jinan-Huanggang Road Tunnel was an engineering marvel, it was also a bold environmental experiment. Building directly beneath the Yellow River, China's mother river, and an ecologically sensitive artery, posed serious environmental risks. Instead of relying on traditional dredging, which often devastates riverbeds, engineers adopted a minimal disturbance approach. As a result, only 15% of the riverbed habitat was disturbed during construction, a fraction compared to standard underwater projects. This decision reflected a growing trend in Chinese infrastructure, building big without leaving a massive ecological scar. One of the most effective tools in this effort was the use of silt curtains. floating barriers deployed along an 8-mile stretch of the river. These curtains trapped suspended particles, stirred up during excavation and material handling, preventing them from drifting downstream and clouding the water. Maintaining clear water is crucial for the over 160 fish species native to the Yellow River, many of which rely on specific light and sediment conditions to survive and breed. By isolating and containing construction debris, crews ensured the river's aquatic life remained largely undisturbed. Excavated material was another environmental hurdle. Each day, the TBM displaced 6,000 cubic meters of sediment, enough to fill nearly 2.5 Olympic swimming pools. Rather than dumping it, the project team ran the spoil through advanced slurry separation systems, which filtered out fine particles down to 0.1 millimeters. A staggering 98% of this material was recycled and repurposed for nearby road construction projects. This approach not only reduced waste and hauling emissions, but also turned byproducts into local infrastructure assets. Even the tunnel boring machine itself was equipped with sustainability features. Thermal sensors inside the TBM closely monitored lubricant temperatures, automatically halting operations if internal heat levels exceeded 3 degrees Celsius, preventing leaks or system failures that could contaminate the river. Noise pollution was also kept in check. Construction maintained levels below 75 decibels, quieter than a household blender, to avoid disturbing nearby aquatic and bird life. From design to execution, the Jinan Tunnel project didn't just carve through the riverbed. It demonstrated how massive infrastructure can evolve to coexist with, rather than conquer, nature. Innovations and patents, born from the project. The Jinan Huanggang Road Tunnel didn't just break records. It broke new ground in engineering innovation, facing extreme time pressure, complex geology, and environmental restrictions. The project team developed a wide array of new tools, materials, and methods to meet their goals. In the process, they filed 43 patents, many of which are now influencing how future megaprojects are approached, both in China and abroad. The 14th Bureau Group, the lead builder behind the tunnel, not only broke size and speed records, they also filed dozens of patents related to tunneling automation, soil stabilization, pressure balancing, and modular ring construction. These innovations weren't just marginal upgrades, they were game-changing solutions born out of necessity. One of the most notable breakthroughs was the development of a new type of high-performance concrete. This proprietary mix hardened 30% faster than traditional formulations, allowing segments to be transported and installed almost immediately after casting. The faster cure rate played a pivotal role in keeping the tunnel's ultra-accelerated schedule on track, especially in cold weather conditions that typically delay concrete setting. The concrete also had enhanced flexibility and strength, crucial for withstanding the shifting pressures beneath the Yellow River. Cooling was another area where innovation shined. Engineers designed a foam-based cut-ahead cooling system that injected a temperature-regulating compound during excavation. This simple but highly effective solution reduced cut-ahead downtime by an estimated 90 minutes per day, allowing the TBM to operate longer with fewer heat-related stoppages. Combined with real-time monitoring, this system kept the machine's performance within a narrow optimal range, preserving efficiency even as geological conditions changed by the meter. Perhaps most impressive were the adaptive automation systems built into Shanhei and its support infrastructure, from the AI that adjusted cut-ahead torque in response to unexpected rock layers, to the modular ring installation routine optimized for speed and accuracy. These systems collectively demonstrated the future of infrastructure: fast, smart, and flexible. The patents filed from the Jinan project range from software algorithms to mechanical designs, laying the groundwork for next-generation tunneling tech. In pushing the limits of what could be achieved in 110 days, the project didn't just solve a city's traffic problem, it expanded the toolkit of global civil engineering. All those groundbreaking innovations paved the way for one final leap, a bold reimagination of what a tunnel could physically become, redefining what a tunnel can be. Most record-breaking tunnels compete in terms of length, but the Jinan Huanggang Road Tunnel broke new ground by focusing on sheer width. With an excavation diameter of 17.5 meters and an outer diameter of 16.8 meters, It holds the title of the widest underwater shield tunnel ever constructed. To put that into perspective, it's over twice the width of the Channel Tunnel, which links the UK and France. This unprecedented scale allowed for a double-decker highway configuration within a single bore, essentially two 3-lane highways stacked vertically, moving 30,000 vehicles daily. Building wide instead of long posed unique technical and logistical challenges that pushed modern tunneling methods to their limits. The difficulty with wider tunnels isn't just the size of the bore, it's the exponential increase in pressure and structural load. Under the Yellow River, hydrostatic pressure was intense, and with a larger surface area, the tunnel walls had to withstand forces akin to 40 adult elephants pressing on every square meter. To manage this, the design incorporated 1.2-meter thick reinforced concrete linings and custom fabricated segment rings, each weighing 72 tons. Unlike in narrower tunnels, stress distribution had to be modeled in 3 dimensions to ensure the double-decked structure remained stable across variable soil conditions. A wider tunnel also complicates boring operations. The massive cut-ahead on the Shanghai TBM wasn't just big, it was one of the most powerful and responsive ever built, equipped with an array of AI-guided sensors to prevent even the slightest misalignment. Over a 5.8-kilometer stretch, alignment error had to stay within 5 millimeters, a feat more difficult in a wide tunnel due to the greater rotational torque and uneven ground pressure. In a narrower bore, minor deviations are manageable. In one this wide, they can compromise structural integrity. The precision required at this scale redefined the technical benchmarks for large-diameter tunneling worldwide. In redefining what a tunnel can be, the Jinan project also redefined what future infrastructure must consider: urban scale, land constraints, ecological impact, and rapid population growth. Wider tunnels like this offer a sustainable alternative to sprawling bridge networks and above-ground highways, especially in dense or protected environments. They also future-proof cities by building for volume, not just distance. The Jinan-Huanggang Road Tunnel didn't just expand a road network, it expanded the boundaries of tunnel engineering itself, proving that going wider may be the next frontier in solving the infrastructure challenges of the 21st century. And that's how China pulled off one of the most jaw-dropping engineering feats in modern history: faster, deeper, and smarter than anyone thought possible. From battling geological chaos to setting world records for speed and scale, the Jinan-Huanggang Road Tunnel didn't just solve a city's traffic crisis, it redefined what's possible beneath a riverbed. If you found this as mind-blowing as we did, make sure to hit that like button, drop a comment with your favorite innovation or moment, and subscribe for more deep dives into the world's boldest mega projects. And don't go just yet. Another epic engineering story is on screen right now. Click it. You've got to see what they pulled off next.